Hello everyone. We'll study chapter 3, computation. Basically, we'll study how to find the maximizer of the observed likelihood function. So this week we'll study the first two sections. So this is the this week. So that is the week 3, and plan to cover it week 4, and then another week for the last two sections. So the problem is to find the maximizer of the likelihood function, and the notation argmax, this argument. So this is the argument, right? So that the value of zeta that maximizes this function, we use zeta hat. Often the MLE can be obtained by solving the score equation. So the equation and the solution. So that means the zeta hat satisfies this. The question is how to find the solution to the score equation. Usually, the score equation is nonlinear. So basically, the question is how to solve nonlinear equations in general. The first method is called the bisection method. So we can start with so suppose we are interested in right. So suppose this is the graph y equal gx. Okay, and you want to find this which value of x it has, and then you suppose you are able to identify an interval, large interval, and then check that the value of g at zeta, so this is zeta 1 and zeta 2. So if the value of g at zeta 1 is negative and the value of zeta g at zeta 2 is positive, then the sign is the sign of the product will be negative. So that means the solution. So that means it actually the root belongs to this interval, right? So we use that. We can actually bisect. Okay. So so this is the bisection. So this is essentially zeta 2 divided by 2. So at this point, you note that the value of g is positive. So this is positive, positive, and negative, right? And so that means the solution should be the root should be in this interval, not the second interval. So you actually make the length of the original interval by half. And so you can keep doing this, right? So keep doing this and check which whether the value is positive or negative. So you can actually reduce the half the length of the interval, and then keep doing that. Then you can keep doing, and so you end up getting a very small interval, and then in the limit, the length of interval will be 0, right? So that's a bisection method. Okay. And the bisection method is very useful in the sense that we don't need to compute the partial derivative and so forth. But it is hard to be generalized when zeta is a vector. So this is more applicable to scalar function. And the second approach is to use linearization method to approximate g as a linear. So another approach is you suppose you can somehow write this is a suppose you can make a so you have a okay, you have a g, right? and you want to find the solution. And then suppose at point, okay, at some point, suppose you have a point, 2 point, okay, so A and B, and then you can basically use these two to fit a linear. Okay, well, this is too good. So so let's use more less. Okay, so suppose this is your and then basically from A you want to fit a line, so you want to approximate this g zeta as a linear function, but so this is a GA, right? So this is GA, and then question is how to fit a line. So this is a line, linear function, and so use linear, and then the question is how to compute the slope. So use this small interval to compute the slope. So you can, this is slope, right? And then solve this, set to 0 to solve this. Okay, so and then that will give a update. So this is updated value. So A is the initial, right, T, and B is the next one, and then zeta is the next one. So something like that. So that is a scant method. So this scant method is a quite classical method until Newton come up with a better method. So the Newton, the second method, so can be sort of the finite difference approximation of the Newton's method. But the second method is developed independently of the Newton's method, and it predates it by over 3,000 years. So basically, now you want to do approximation, linear approximation using differentiation, right? So this is linear, and then slope. So this is slope, and we now use differentiation to compute the slope. Okay, and if this is a scope function, then the differentiation of the scope function minus is information, right? Fisher information function. So for the scope function, we have this form. Okay, so here's a graphical illustration of the Newton's method. So this is the initial point, and then you fit the tangent, right? You compute the slope, and then find out the root. Find out the root of this tangent line, and that root is an updated value. Okay, and then use this one to fit another tangent line, right? And then find the root. So you can keep doing, you can continue to get this updated, and then in the end it will converge under some conditions. So and then R.A. Fisher noted that the computation using Newton's method to obtain the MLE can be unstable because the information, Fisher information, is a random variable. Okay, so you can actually stabilize it by taking the expectation. Okay, so for example, it is possible that the information can be singular even even though the expectation is non-singular. So the Fisher scoring method stabilize the computation by taking the expectation, right? So that makes computation more stable, a little bit more stable. And one problem with the Fisher score method is that the sequence of the solution does not necessarily increase the likelihood function. So if you're doing this, okay, so here's a so this is the likelihood. Okay, let me write it in the next slide, next page. So suppose this is the likelihood function, okay, and then this is the L theta, and then those score function, the score function is then this is the slope is positive, right? So positive, and then so this is not really this is too good, maybe right, something like that. So suppose we have something like this. So this is the graph of the scope function, and then see if you start with here, okay, if you start with a point here, then you have a tangent here, okay, and then you have a tangent here. So the update will converge like getting closer, okay, to the root. But if you start with here, okay, if you start with here, then it's possible. So then you have this one, and then you have you might in some point it's possible that this tangent can go far away from the center, so from the true root, right? So that means what you are, so you here this is your initial, and then this is a theta 1, and then you have a theta 2, and then your theta 3. Theta 3 can actually go outside of the theta 1. So then that's not good, right? So basically you want to climb up rather than going down and going down. So that so maybe so why that happen? Because we basically why we go down, because we move too far away. I mean, so we can actually reduce the distance and stop here, right? Stop here. Then you might be better. So basically ascent method makes sure that your likelihood increase. So you want to make sure that you goes up rather than going down. So that is the idea. So basically you if that happens, if it turns out that your initial point, so your updated one actually reduces the likelihood, then you reduce the alpha, okay. So that's sometimes that is called a learning rate. In machine learning, they call it learning rate. So you want to reduce the learning rate to make it improve, to increase the likelihood. Okay, so that is the ascent method, and cosine Newton method is a way of avoiding the partial derivative of the function of the scope function. So the choice of m is essentially is relatively unimportant. Okay. So example 3.1 present an example for the logistic regression model. You can work out. So this is pretty quite simple model, right? So I think we already covered this, but probably better. It would be better if you work out and see whether you get the same answer. So that's something you can try. And basically, the Newton-Raphson method. There's no. So this is Fisher information is free of y. So that means your expectation here was originally for y given x, but there's no y. So that means it's the same. Okay. So Fisher's Newton-Raphson method taking Fisher scoring method is actually take this method, right, using the expectation, while Newton-Raphson method is using this original information function, but they are the same. And so that's this example. Okay.